New chapter, Applications of Integration. Welcome. Section 7.1, Area of a region between two curves. So in this section we'll study how we can find areas not between a curve and the x-axis, but between two curves. The objectives are to find the area of a region between two curves using integration, to find the area of a region between intersecting curves using integration, and finally, to find the area of a region by integrating with respect to y. So a reminder of what it means when we integrate. The method of finding areas is developed as an accumulation of areas of rectangles whose width approached 0. Here we have a rectangle. The width or the base is delta x and the height is f of x. So if we want to find the area of this rectangle, it's base times height, and it means delta x times f of x. So the area of one rectangle is f of x times delta x, base times height. When delta x approaches 0, when it becomes infinitely narrow, we stop using delta, we write it dx, and it's dx times f of x. This is base times height. And the integral sign here means that we are adding an infinite number of these rectangles. So it's an infinite sum. It's going to be useful to remember this, and especially this figure here with a rectangle, when we study more applications of integration in sections 7.2 and 7.3. So example 1, find the area between y equals secant squared x and y equals sine x from x equals 0 to x equals pi over 4. First thing we need to do is to sketch the graphs. This is what it looks like. Y equals secant squared x is above, y equals sine x is below. We will integrate from 0 to pi over 4, so this is the area we are trying to find. This is a much better graph. The graph on the right is really just a sketch, but it's good enough for what we need to do. But on the left we have an excellent graph of these two functions, and on the right now we can see the area that we're trying to find. So how are we going to do that? It's not really anything new. You can do it, you can find yourself the technique. The idea is to look at both of these functions separately, and we know how to find the area between a function and the x-axis. That means we know how to find the purple area on the left here. It's just the integral from 0 to pi over 4 of secant squared x. And then we'll subtract, again using something we know, we'll subtract the orange area here, which is the integral from 0 to pi over 4 of sine x. And when we do this area minus the orange one, we'll find what we are looking for. So back to this exercise. The integral from 0 to pi over 4 of secant squared x, which is the top function, is here, and we're going to subtract the integral from 0 to pi over 4 of sine x. Using properties of integrals, you can, and you probably will, start writing this not as two separate integrals that we subtract from each other, but simply as one integral from 0 to pi over 4 of secant squared x minus sine x. So very often this is the only line that we're going to see in your work, but it's very important to remember that it comes from something like that. It's an area minus another area. Now we just need to solve. The integral of secant squared x is tan x. The integral of negative sine x is cosine x. We can substitute pi over 4 and substitute 0, and it becomes tan of pi over 4 plus cosine of pi over 4 minus tan of 0 plus cosine of 0. Finally, we get that this area is root 2 over 2, which is approximately 0.707. Example 2, find the area enclosed by y equals 2 minus x squared and y equals negative x. First step, again, make a sketch. You need to see what we're talking about. And here we see that we are not given the lower boundary and the upper boundary. It's not like integrate from x equals 0 to x equals pi over 4. It's just the area enclosed by these two curves, so we will need to find this intersection and that intersection, and we will integrate from x equals here to x equals that value, the first coordinate of the intersection point here. One more detail before we move on to finding these intersections and finding the area. You may notice that you may have been surprised with this area here being below the x-axis, so it may have given you the impression that we have to be careful, we're going to have a negative area and we have to change the sign. We don't have to. When we're looking for areas between two curves, as long as one curve is above the other, this one is below, we just always do area integration of this curve minus that one, and we don't have to worry whether we are above or below the x-axis. We'll see later what the equivalent of areas above and below the x-axis means when we are finding the area between two curves. So no problem if this area is partially below the x-axis. So what are the intersect of these two curves? We need to find the x values. We set up the equation 2 minus x squared equals negative x. It's a quadratic equation, so we move everything to one side and we either factorize, or if we can't factorize, use the quadratic formula. Here it's easy to factorize and we find x equals negative 1 and x equals 2. That means we have to integrate from negative 1 to 2. You can see here that I only wrote one integral, the integral from negative 1 to 2 of the curve that is above minus the curve that is below. 2 minus x squared minus negative x is 2 plus x minus x squared. That's a polynomial. It's the easiest ones to integrate. It's the integral. It's 2x plus half x squared minus 1/3 x cubed. That we now need to substitute x equals 2 and x equals negative 1. You know how to do that. And we finally get that the area is equal to 9 over 2. So a nice number, 4.5, for this quite complicated area. If you have to find the area of the region between two graphs that intersect in more than 2 points, like you can see on the illustration here, you need to find each area separately. So we're going to have to integrate from here, x equals negative 2 to x equals 0, and then we'll have to integrate from x equals 0 to x equals 2. Why is that? Because the curve that is above changes. Here, the curve that's above is the pink curve, and then from 0 to 2, the curve that is above is the blue curve. So we need to study each area separately, A1, A2. A1 is going to be the integral from negative 2 to 0 of the purple curve. You can't, well, here's the equation, it's given here. 2x cubed minus x squared minus 5x minus the equation of the blue curve. For the second area, I just simply flipped the blue and the purple. Now it's blue minus purple, or blue minus pink. And this time, for that area A2, we have to integrate from 0 to 2. And therefore the area between the two curves is simply a1 plus a2. I didn't find the exact values, it doesn't really matter, it's just an example. You can also use absolute values if you are using your calculators and integrate the absolute value of one curve minus the other, and it will work. It's a little bit of a brutal way of doing it, but it works. So in example 3, we'll have to find the area of the region in the first quadrant that is bounded above by y equal root x. So it's the area, the region that is bounded above by this, and bounded below by the x-axis and this line. So it also says it's the region in the first quadrant. Read these exercises carefully so that you find which area you're really looking for. This is the area we want to find, and I broke it down into two parts. We will first integrate from 0 to 2, and we won't need to care about this line for the first area. This is simply the area under the curve of y equal root x. And then, second part, we will integrate from 2 to 4 of y equals root x minus 2. So this x equals 4, I wrote it already. We are not supposed to know it, but we can find it by solving. X minus 2 equals root x. I take the square, put like terms together, factorize, or use the calculator, or use the quadratic formula to find x equals 4 and x equals negative 1. X equals negative 1 is an extraneous solution, so this x equals 4 is the first coordinate of the intersection that we needed. Now we'll integrate a1 to find a1 first. a1 is the integral from 0 to 2 of root x dx, and we find that it's a 1.886. a2 is the integral from 2 to 4 of the curve above minus the curve below. Using the power rule, we can find the integral easily. We substitute 4 and we substitute 2, and we get that a2 is 1.448. Therefore, the area in quadrant 1 that was defined is a1 plus a2, which is 3.333. It looks like maybe it's a third of something, 10 over 3. If you actually do the computations more carefully, you will see that it's not, but it looks like this. So if you felt that this might be a third, I appreciate that you had this intuition, and then when you look more carefully, or if you check more decimals, you realize it's not. The way I decided to break down this area is not the only way to solve this exercise. I'll mention one, and then we'll see another way. The other way you could have done it would have been to find the area between the two curves from x equals 0 all the way to x equals 4, which would have given you this whole area here, and then you could have subtracted the area of this triangle, and you would have found the same value, obviously. So there's more than one way to solve this exercise. Actually, there's a third way that we're going to use now, using integration with respect to y. What does it mean? It means that when you integrate, instead of having these vertical rectangles where dx is the width and it becomes smaller and smaller, infinitely small, we are actually going to integrate with horizontal rectangles. And the width that is getting closer and closer to 0 is the dy. So if we want to do that, we need to change the equations and solve them in terms of y. So y equals root x, the equation of the first curve, becomes x equals y squared, where y is greater than 0. The other curve, y equals x minus 2, becomes x equals y plus 2. So these two equations define the exact same curves, but this time it's in terms of x. So using a horizontal rectangle, we're going to have to subtract curves and figure out which curve is above the other. Since we have changed x and y, and we are focusing on y, we need to look at this arrow. This arrow shows us where the above curve is. The curve that is above in this example is the line. It's higher in terms of the right direction than the square root curve. So if we integrate, we will integrate y plus 2, the line, minus y squared, which is this half parabola here. I haven't written the boundaries yet, because since everything here is in terms of y, we integrate y plus 2 minus y squared dy. We also need the boundaries to be y values, and therefore we have to look at the y value of the intersection. We're not going to integrate from 0 to 4 or from 2 to 4. We're going to integrate vertically from 0, piling up horizontal rectangles until we reach y equals 2. That's why the boundaries are 0 and 2. But from here on, it's not hard anymore. It's just a polynomial. So the integral is half y squared plus 2y minus 1/3 y cubed. We substitute y equals 2 and y equals 0, and we find, obviously, the same answer. So what are the pros and cons of this method of integrating with respect to y? Well, the benefit is that it's shorter. We only had to integrate one area. We didn't have to break this region into two parts. We could just integrate at once. The disadvantage, of course, is that it's a little confusing. It's new, and we're not used to integrate in terms of y. Let's try another example of integration in terms of y. We want to find the area of the region enclosed by the graphs of y equals x cubed and x equals y squared minus 2. This is what it looks like. This isn't even a function, but it doesn't matter. And the area of the region enclosed by the graphs is this area here, right? It doesn't have a single straight line, but it's a well-defined area. Now we could integrate in terms of x, and I invite you to try if you are brave enough, but it's going to be really annoying. Especially, it's going to be annoying in this part here, because we are integrating a square root minus the same function below, so it's really going to be hard up to this intersection point. It would take several steps until we break down this red area, this red region, into proper areas and find each of them separately. Much easier is to integrate in terms of y. If you now look at these two curves and focus on looking at this as the top, we see that it's much easier. This curve here is above the parabola from one intersection point all the way to the next one, and it's therefore going to be much easier to use horizontal rectangles. So we need to change these two equations in terms of y. Y equals x cubed is x equals cube root of y. The other one was given, x is y squared minus 2. If we wanted to try to integrate in terms of x, this is what we would have to use. So using the calculator, we can find the intersections, and the intersections are -1, and 1.215, 1.793. So see how this is easy now. If we just trust that we know how to do it, we're going to integrate the curve that is above, which is x equals cube root y, minus the curve that is below, x equals y squared minus 2 dy. And we just need to define the boundaries, so I'll give you a second to figure out what the boundaries are. Okay, I hope you made a decision. So the y values of the intersections are -1 and 1.793. So -1, 1.793. We are piling up rectangles from here, y equals -1, all the way to up here, y equals 1.793. From here it's easy. Well, here I just used a calculator, but we could still do it manually using the power rule. So the area is 4.215. That's all for section 7.1. Let's review the objectives. Find the area of a region between two curves using integration, is what we did here and many times afterwards. So remember, always top curve minus curve below. Find the area of a region between intersecting curves using integration. You need to break down the region into separate parts if the curve that is above changes. And finally, find the area of a region by integrating with respect to y. We pile up horizontal rectangles, so the width, the infinitely small width is dy. The height of the rectangle is, in this example, y plus 2 minus y squared.